Hi, AP physicists. All right, we're going to get started and do a little physics now that hopefully you're home safe and sound. You made it back despite all that scary ice and all of that. Low coefficient of friction does not make driving a fun thing. All right, let's focus on some waves here for a little bit. So this is the information that I was hoping to share with you during class today, but our plan got a little bit derailed. So we are going to talk about waves, wave reflection, and put that together with superposition to get ourselves into some new interesting content. So we're going to start just with a little bit of information about waves traveling in a medium and then what happens when they hit a barrier. So I want you to imagine, because we were going to do this demo in class today, which kind of makes me sad. I want you to imagine we're all sitting out on the hallway floor, and I've got a long slinky that I've stretched between my hand. So there's my hand, and then somebody else, some lucky winner. So there's this nice little long slinky, long, so long. And then somebody else's hand is over here. So they're holding onto that slinky. So we've got it stretched. And then along the floor, I'm going to send just one wave pulse down. Okay, so I'm going to displace the slinky just a little bit. And in doing so let's imagine that I displace it in this direction. Okay, that wave is just going to travel right down the slinky, okay? And as it goes, it's going to go with the same amplitude all the way down until it hits the barrier. And by barrier, I mean a change in medium. I'm just going to write that down. Barrier is a change in medium. So interesting things happen when a wave hits a medium or a change in medium. The mechanical waves obviously need a medium to travel through. So when a wave hits a barrier, some of the wave, we'll say some of the wave will reflect, which means that it will go back into the original medium, and some will be transmitted. So some of the wave will reflect, some of it will be transmitted into the new medium. So you have some evidence of the wave being transmitted into the new medium. Just thinking of a couple of examples. One would be if you are in a swimming pool and you are underneath the water, you can still hear people talking outside, people that are on the edge of the pool or whatever. You can still hear them talking. It might be muffled and might sound a little bit funny, but you know that that sound wave can go from the air, which is where the sound was generated, and into the water. So that would be a little bit of evidence of the transmission into the new medium. Another way that you could think about that is if you imagine that you were the lucky person over here that was holding on to the slinky. When that wave got down to the end of the slinky, you would feel that. And by feeling that, what's happening is that some of the wave is being transmitted to you. So some of that wave is being transmitted into the new medium. And that wave, just a couple pieces of information about that. Generally, it's going to have a little bit of a smaller amplitude, but it will. So some of the energy is transmitted. Some energy transmitted. And one thing that's really important to know about it is that, let's say instead of sending one pulse down, I send pulse after pulse after pulse after pulse, right? So it's got a constant period or a constant frequency. If you happen to be the person holding onto the other end of that slinky, you would feel the wave coming in at the same frequency, okay? So some of the energy is transmitted, and the big thing to know, this is like if you're going to know one thing about transmitted waves that you really need to know, it is that the frequency, come on, stinker. There we go. The frequency of the transmitted wave is the same. The same. Frequency does not change when you hit a barrier in the medium. Or a medium change, a barrier. Okay, so that's super, super important to know. I'm going to highlight that in yellow because I don't want you to forget that. That's one of those things. Put big stars and glitter pens on that one because that's important to know. Beyond that, we're going to kind of leave the transmitted waves for another time. The thing we're going to really focus on today is reflected waves. So that's the part when I send this red wave down that I've got here, when it hits the barrier, some of that wave is going to bounce back, and we want to know what's going to happen to it. Okay. Now, the fun part of that, one of the things that we need to know about that is that it will also have the same frequency. Okay, because again, it's going to come back and back and back and back. But when it reflects, the nature of the wave, and by that I mean, will it be above the equilibrium or below the equilibrium, actually depends on the type of barrier. So there are a couple of ways to talk about that. One is to say that you have a medium that is more dense or less dense. Another way to talk about that is saying that you have a fixed end, or if you have a loose end. Okay, so a fixed end would be like if somebody's actually holding on to it. A loose end would be if you're like holding, like a big rope or like a jump rope, I kind of imagine, and you just send a wave down that, but nobody's holding on to it at the other end. There will be some bounce back as well, and that will be interesting and different. So I've got a couple of quick videos to show you to give you a sense of what happens there. These are courtesy of, I don't even remember, some school, but we'll take a look. So these are not with a slinky like we were going to use. It's actually on something called a wave demonstrator, like legitimately just made for physics teachers to teach these beautiful things. Okay, so it's a bunch of little metal rods that are balanced, and then we can send waves down it. In the first one, there's a fixed end. So that means that the end of the apparatus is held in place. So this is like if you're holding on to the other end of my slinky. So here we go. We're going to give this one a shot. We'll watch it together. So they're going to send a pulse down. It's up, 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 up. And then you'll notice when it reflects off of this end here, okay, then it bounces back and it goes down. It's actually thanks to Newton's third law that happens. We can go through that sometime if you would like to. But the thing that we need to know is that when that reflection happens, so again, we're talking about the fixed end. In this case, with the fixed end, we can say that the reflected wave is inverted. Okay. You may be able to predict, based on the thing the fact that that's what I really wanted to pay attention to, that there may be a different situation when we have the loose end. So now in this case, when we watch the loose end, instead of that stick being there to hold on, it's just going to be allowed to bounce. Here we go. So same apparatus. I'll do it in slow-mo for us to see. So it goes up, 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 up. It hits that medium change, and it bounces right back up. That's amazing. It's amazing how that works. So we're going to write that down on our sheet as well. So for a loose end, instead of the reflected wave being inverted, we're just going to say that the reflected wave, I'm going to say, stays on the same side of equilibrium. Okay, so that's one of those things that I know I've seen on the AP exam a few times, is delineating between those two. So the way you can kind of think about that is that it's going to pull on that fixed end. For the fixed end, it's going to pull back, and that's why it's going to be reflected in an inverted fashion, whereas the loose end, it's just going to be able to go wherever it wants, and so it's just going to bring it right back in the same direction. Okay, so that's important. And then the other thing, again, that I want to make sure that you know is that anytime that a wave encounters a change in medium, does the frequency change? No, no, no. I hear you all saying it really loud because you know it and you feel passionately about it. No, when a wave hits a barrier or a change in medium, the frequency does not change. Don't forget that. It's important. Okay, so that's one of the big things, is reflection, that I want you to know. And the other little piece that I want to make sure that you're aware of, you did this in a couple of your exercises from the last cold days, but I just want to make sure you understand, because we're going to need it moving forward, is the speed of sound, or not the speed of sound, but the speed of a wave. Speed of a wave. Okay, so let's talk about the speed of a wave. We know speed. We've been doing this since the beginning of the year. Speed or velocity is just distance over time. That's all well and good. But when we talk about a wave, we like to talk about it in terms of our wavy sorts of things. So when we talk about a wave moving, so there it is. And if we've got more than one wave, like let's say we have this periodic wave that's traveling down, instead of just talking about the distance that one travels, we can talk about the distance over time during one cycle. So the distance that a wave travels in one cycle would be from crest to crest or trough to trough, that thing known as lambda, or the wavelength. So we can say the velocity is equal to the wavelength. Sure. And again, if it's during one cycle, how long does it take for a cycle to happen? I know, it's the period, right? So we've got lambda over t. That is a form of, they call this very formally the wave equation. But as most people do, we're not huge fans of denominators when we can avoid them. So instead of using over t, because we know that the inverse of period is just frequency, we can write this as lambda times f is equal to speed. So this is what they call the wave speed equation. I'm using big air quotes when I say that because I think it's kind of funny, but it's just lambda times f. It's just talking about speed. Okay. So those are the big two background things. Now we're going to jump into what we really care about. So this can all kind of go together there. What we're really getting into today is an addition problem. So yesterday when we talked about superposition. That was two waves that exist in the same place at the same time. And unlike matter, waves can exist in the same place at the same time. And then we've got reflection. Reflection was just what we talk about when you have a wave that hits a barrier and then bounces back. The fun thing is that when you add superposition and reflection, you get this funny looking guy here. I like that picture because it reminds me that it is anybody want to say it? It's a standing wave. Ha 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 ha. Get it? It's funny. I thought it was, at least. Hopefully you did too. All right. So I'm going to show you another quick video that does a nice demo. And then we'll do some derivations here so that you understand where this is coming from, how the math works, and what we're going to do tomorrow. So here we go. So this is another video courtesy of some college or something where they make these awesome videos and have time to do that. Yay. All right. Reflection and interference. As I send a single pulse down to this fixed end, you can see that it reflects upside down on itself. Okay, so that's what we just talked about, right? So this is like the big long slinky that I have in my back room. So if we send a wave pulse, I'll go back one more time so you can just kind of see that, because sometimes it is a little overwhelming. So here we go. So UCLA Department of Physics and Astronomy, thank you so much for making this video for us. So he's going to send a pulse from here. He's going to send it, I can't remember if it's up or down, and then this grad student over here is holding the wave, and holding the slinky. If you watch his hands carefully, you can see that some of the energy is being transmitted to his hands, but most of it is being reflected. Here we go. Reflection and interference. As I send a single pulse down to this fixed end, you can see that it reflects upside down on itself. If I send a rhythmic pulse, it reflects on itself. This is the fundamental mode. This is the fun part. Here we go. At twice the frequency. Actually, we're not going to do this yet. I'm going to make you wait for it for just a minute. We're going to go ahead and do that beginning part to start here. So superposition plus reflection gives us this standing wave business. So what does that mean? Well, let's draw a picture here. So a standing wave. We'll watch the video. Sorry, I keep changing my mind because I like doing this before, but we'll do it this way. Here we go. Oh, it's so cool. Look at that. In the second harmonic. Do you see that? How that there are places like right here where he's holding on it, and right here where he's holding on it. And then there's this place right in the middle. I don't know if you can see where I'm pointing, but right in the middle where that slinky does not move. It's amazing. That's physics right there. Here we go. We'll watch it again. Look at that. If I triple the frequency. You ready for this, friends? Holy cow. What? Third harmonic. Third harmonic. What does that mean? I don't even know. Well, I do, but we'll talk about it in a second. Look at that. That's a standing wave right there. Hot diggity. Let's talk about what that means. So he did just 3 different things there. The first one, the thing he called the fundamental. wave, okay? The fundamental wave. His grad student friend was holding on here. He was holding on here, and the wave looked like this. Now, where did that come from? They weren't both shaking the slinky, only one. So this guy sent a pulse down, and when it got to his friend that was standing here, that pulse reflected back. And so we've got one pulse going with an amplitude that's up above equilibrium and another one that's going down below. And those two pulses, if they are timed just right, are going to result in lots and lots of constructive interference right here. Okay? Whereas when he moved it with a faster frequency, so here is his friend's hand and here was his hand, okay? It went up and down like this. This is this cool standing wave stuff, you guys. It's so neat. So it's called a standing wave, standing like it's not moving, because if you look at it very carefully, it looks like it's just sitting still, but it's not. It's actually moving really, really fast. So you've got these 3 points here where it doesn't look like it's moving, and those places are called nodes. That's a node. That's a node. A node is a place in the medium of no movement. Okay. And then these other places where you have maximum movement, okay, where there's a lot of constructive interference, whereas again right here, so this is destructive, 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 they subtract out. These places of constructive interference are called antinodes. And from our English background, we know that anti just means the opposite. So instead of no movement, it's like no movement would be a whole lot of movement, okay? So we've got fundamental, we've got first and second harmonics, and it's all this kind of crazy stuff. So now we've got to do some math with it, because this in and of itself is pretty straightforward. We can imagine then a third and a fourth and a fifth. And we do this, number one, because it's fun. We can do this with our slinkies. But this whole principle is also what drives all of music, okay, and a lot of other things, but music is really where we think about this a lot. So we're going to talk first about the stringed instruments. So when I'm talking about stringed instruments, I'm talking about like violins, violas, cellos, bass, that kind of thing, guitar, and all of those also included, okay? A standing wave on a string. Here we go. So the simplest standing wave that we can have is going to have 2 nodes on either end. So that's the 2 places where the string is connected to the instrument, okay? And then the standing wave is going to look just like we drew it before, like this. Again, with 2 nodes. Go ahead and label them as nodes. And between every 2 nodes, you're going to find an antinode. Okay. Now, when we talk about the note that an instrument plays, remember we talk about the note as the pitch, and the pitch is related to the frequency. So frequency determines, I don't know why I can't spell today, I'm sorry. The pitch or the note that's being played. Okay, and there are a few different ways to affect the frequency of the note that's being played. One is by tuning the instrument, and we do that by changing the tension. On the string. So I am not a string instrument player, but my best friend is, and she plays the violin. And when she uses the little tuning knobs at the top of the violin, that changes the tension in the string, and then that can affect the note that's being played. Okay, so that's one way to do it. And once we have a certain tension, then we can figure out what frequency we will get on a standing wave on the string. So let's figure out how we might do that. So we're going to look at that. This is where we need our wave speed equation, which is why we talked about it a minute ago. We can talk about the length of the string, because that's the other way to change the note. So I was going to say that, sorry. So you can change the pitch based on the tension, but you can also affect it by changing the length of the string. If you could only affect it by changing the tension, then it would be very inefficient to play more than one note at a time because you'd have to, tune it, tune it, tune it. But luckily for us, you can also put your fingers at different places on a violin, viola, guitar, whatever, and it changes the length, and that length then determines the note that's being played. So we're going to call the length L, okay? And we may notice here that length, if we kind of draw it out further, we can figure out how that length compares to the wavelength of the wave. So if we look over here, I just tried to highlight a complete wavelength of the wave. So it's going to go from equilibrium up, down, and back to equilibrium. And so from that, we can see that the length of the string, that little green line that I've drawn, is really half of a total wavelength of that wave, okay? The wave that is being generated on the string that is then going to resonate inside the body of the violin or whatever instrument and then out to your ears. Okay, so we can say that L is equal to 1/2 of lambda, or again, getting rid of our denominators, we can say that lambda is equal to 2L. So that's all cool. We're going to remember that we talked earlier about the velocity equaling the frequency times the wavelength. We can then solve that for frequency. So frequency is equal to velocity over lambda, or we can say here then that frequency is equal to the velocity of the wave over 2L. So the length, again, is one way that I can change the frequency, and velocity is determined by the tension in the string. Okay, so given a certain tension, we can find the velocity, and then from that, the length is determined, the length determines the frequency. So that's all well and good. And honestly, when you're first learning an instrument, most of what you're doing are these basic, simple standing waves. And this here, I'm going to put a box around it, maybe, there we go, is known as the fundamental frequency for that situation, okay? The fundamental frequency, sometimes we call that F1. Now, that's not a very exciting standing wave, and if we're going to make things a little more interesting, then we need to draw a more interesting standing wave. So I'm going to draw my two nodes where the people in the lab were holding on to the slinky, or where the knob and the end of the violin are, okay? And now instead of just having two nodes, though, I'm going to put another node right in the middle. So I've got a node out on each side, and I've got a node in the middle, and then I'm going to find antinodes on either side of those nodes. So now I've got this cute little standing wave with two antinodes and 3 nodes. Okay, so now this standing wave looks a little bit different than the one above. We can do the same kind of process here, though. We still have the same length of string, more or less, okay? But now, if you look carefully, if we look at that wavelength, the wavelength, is equal to L. Okay, so L and lambda are equivalent now. So we can say that if we take this one step further, just kind of doing the same thought process that we did before, V is equal to F times lambda, and we can say then that F is equal to V over lambda, and then we could just say then that F, and this is the second harmonic, the second frequency, is equal to V over L. Now, that's all well and good, but if you have the opportunity, why not multiply by a form of 1? So I'm going to multiply by 2 over 2. Why not? I don't know. I'll show you why in just a second. This is why we're going to do it, because then we can say that F2 is equal to, I'm going to pull this 2 out in front, times V over 2L. And the reason I do that, my friends, and it's kind of goofy, because otherwise you're like, what is she doing? Why multiply by a form of 1? It's because, if you haven't seen it yet, let's put it in here, V over 2L, V over 2L. So we can say that the second frequency, okay, F2 is, then we could also say F2 is equal to 2 times F1. So far, so good. We happy? So there's a little bit of a pattern, but 2 points does not make a pattern. So let's take it one more step. So we're going to do a little bit more complicated standing wave. So instead of having just 3 nodes, we're going to add a fourth. Now, whenever you have a standing wave, the nodes are always going to be evenly spaced. So we're going to put one in like that. And now we've got 4 nodes, four nodes. And that means it will have 3 antinodes. So the number of antinodes and the number of nodes is always going to be off by 1. So node, antinode, node, antinode, node, antinode. I got ahead of myself there. All right. And so I just kind of write that out so you can see it. And then we're going to mark our length. So we're doing the same thing that we did the last time. We're just trying to develop a pattern so that we can figure out how to express these frequencies of these different standing waves. So there are our nodes and antinodes on our third harmonic, our third standing wave. And now I'm going to highlight just one wavelength. And I'm going to stop short. I'm going to stop before I get to all the way to the end. So L in this case is not equal to a wavelength, but L is actually equal to how much of a wavelength? Oh, it looks like it's 3/2 or 1.5 wavelengths. Well, that's fun. Take that one step further, say that lambda then is equal to 2/3 of L. So far, so good. Some of you may see where this is going, and if you don't, that's okay. I didn't the first time I did it either, but we can do it together. V is equal to F times lambda. So that means that we can say F is equal to V over lambda. I'm just writing it out every time because it helps me to see it. We can say that F, there should be an equal sign there, sorry about that, is equal to V over 2/3 L. Ooh, denominator of a denominator. What happens to that? I know. Yeah, F3, the third harmonic, is equal to 3 times, wait for it, V over 2L. Look at that. That's so cool. Do you see the pattern developing? Let me zoom it out a little bit so you can see it. Holy cow. So we've got the first harmonic. This is the first one. Is V over 2L. You've got the second harmonic, 2 times V over 2L. And the third harmonic is 3 times V over 2L. Now, as clever physicists, we can make some sort of generalization here, can't we? We can say that for a standing wave on a string, any frequency, Fn, so the first harmonic or the third harmonic or the seventh harmonic. Now, from a musician's perspective, things like the seventh harmonic sound ridiculous. But from a physicist's perspective, in a theoretical world, absolutely this makes sense. And in standing waves and other things besides musical instruments, that is absolutely a thing. Okay, so the nth harmonic, if you will, we'll call that the nth harmonic, okay? Fn is equal to, it's going to be whatever your n is, times the velocity of the wave, divided by 2 times the length of your string, okay? So that is the equation for standing waves on a string. Now, it's a little bit funny, and I'm kind of rushing because I told you it was going to be a short video, and I've already lied to you. I apologize for that, okay? But this is one of those things that we're going to use, and we're actually going to use the next piece of this tomorrow, so I want to make sure this makes sense. So from a musical perspective, we have now covered the string part of the orchestra, but many of you are in band, not in orchestra, and I guess we've covered some percussive instruments as well, and we can make some arguments about how that all works another time, but for right now, mostly just strings. But many of you I know play wind instruments, and so for you wind instrument people, we have to think about how things are a little bit different.